All right, let's talk about problem solving. So I've included I've included a file with this lecture, so you can print this off and kind of take notes as we go. If you would like to do so, it's not mandatory, but that's how I would suggest that you use these notes. So I won't necessarily have a print off for every single lecture. In fact, most of the time I probably won't. But for this particular lecture, there was just a lot of writing that we would have to do, so I prepared this handout. Anyway, so feel free to kind of print this off and fill in the blanks as you watch this video. Problem solving is a big part of what mathematics is. We do a lot of problem solving in math, and this happens to be kind of a weakness of a lot of students, and so I think that it gives you sort of a skewed idea of what math really is, because oftentimes you're just doing a lot of symbolic manipulation. You're just moving symbols around a page, but it's completely devoid of meaning. And with math, it's really not actually like that most of the time. So anyway, so I want to talk about problem solving a little bit. George Polya was a famous mathematician. He collaborated with a lot of other mathematicians, and he was also well known as a really good teacher. And so he wrote these problem-solving steps, and I think they're good. I think it's a good place to start. If you're the type of person who finds yourself getting stuck on when you're doing kind of problem-solving stuff, these are good suggestions to keep in mind. So let's read through them together, right? So the first step is to understand the problem, and that might seem a little bit obvious, but you'd be surprised. I mean, students skip this step all the time. In algebra class or whatever, they'll read through a problem, but then they won't understand it. But they'll immediately start to try to jump to some kind of equation or formula or something like that to try to solve the problem that they never understood in the first place. You should take a lot of time in step one and make sure you really have a firm grasp on the problem. You'd be surprised how much that helps you and how much time that ends up saving you. If you'll invest a lot of time here, then the rest of the problem will go a lot more smoothly. And overall, you'll spend less time on the problem. So step one is to understand the problem. That means you have to read the problem. You may have to reread the problem. In fact, most of the time, I have a master's degree in mathematics, and even when I'm reading like a basic algebra problem, I'll still have to read it 2-3 times in order to grasp what's going on. So read it, reread it. A good way to know if you understand the problem is if you can restate the problem in your own words. So try to restate the problem in your own words, and if you can't, well, then you don't understand the problem. Go back and read it again, right? And then don't just guess at a solution. Don't just try to rush to start solving the problem. Make sure you get a thorough grasp on what is happening. Step two is to then devise a plan. And actually, what we're going to do in this lecture is we're going to practice some strategies that you can employ when you're devising a plan in step two. The plan may involve setting up an algebraic equation or drawing a figure or doing something else that comes from your catalog of math knowledge. And it might require some creativity because not all problems are going to succumb to the same approach, right? Step three is then to carry out the plan. And that's the easy part. It's also the part that students try to jump to. but it's the easiest part by far. So this is just doing what you planned to do in part two. And then step four is to check your answer. Once you think you've solved the problem, go back and determine if your answer fits the conditions originally stated in the problem. Make sure that it's actually an answer to the question. And then also make sure that your answer makes sense, right? So, for example, if you're trying to find the number of people who participate in Winter X Games, 19.5 would not be acceptable, right? Because you can't have 0.5 people. Maybe there's a pregnant woman. I don't know. But no, 19.5 doesn't make any sense. Or in an investment problem, it's very, very unlikely that your $1,000 deposit would earn $334 of interest in 1 month, right? So check your answer. Make sure that you answered the question, first of all. And then second of all, make sure that your answer makes sense. Another thing that you can do when you're checking your answer is if you thought of more than one way to try the problem in step 2, then maybe try out the other way that you thought about doing the problem. And if your answer is correct, I mean, you should end up with the same answer both ways, right? So if you do the problem in 2 different ways and you get 2 different answers, well, then you know something went wrong somewhere, right? But if you get the same answer using both approaches, then you can be a lot more confident that what you did was correct. So anyway, those are Puglia's 4 steps. I'll usually call these Puglia's 4 steps. But what I want to do is walk you through some strategies that you could employ when you're devising a plan here in step 2. So let's do it. So this first one, the first strategy is trying to visualize a condition in a word problem. So this one says 4 campers, Adlia, Benjamin, Christine, and Dari have just arrived at the Seeds of Peace camp in Maine for an orientation session. Each will shake hands with all of the others. Draw a picture to illustrate this situation and determine the number of handshakes. Okay. Now, some of you, no doubt, are really great artists, and you'll actually sit there and like draw people and stuff. I'm not going to get anywhere near that detailed. I'm just going to represent each of these people with a dot, right? So I'm going to call this first dot. This is Adlia, and I'm just going to label it A. And this dot I'm going to call Benjamin, and I'm just going to label it B for Benjamin. And this dot will be for Christine, which I'll label with a C. And this dot will be Dari, which I'll label with a D. Now, the idea is that each person wants to shake hands with all of the others, right? Each person wants to shake hands with all of the others. Well, so I can just represent this with some lines, right? If A is going to shake hands with B, then that means there's 1 handshake. A also wants to shake hands with C, and A also wants to shake hands with D. Right? Now notice that A shaking hands with B is the same thing as B shaking hands with A. And so the picture that we're drawing here is pretty nice because we only want to count that handshake once, and there's only 1 line segment connecting A and B, so that's actually really nice. Well, who else should B shake hands with, right? B shakes hands with A, but B also should shake hands with C, and B should also shake hands with D. Okay. Now C needs to shake hands with A, that's already done. Needs to shake hands with B, that's already done. And then needs to shake hands with D. So we'll draw in that line. And that should take care of C. And now D needs to shake hands with A, done. B, done. And C, done. So by the time we get to D, all of the necessary segments are already drawn in. So we can answer the question pretty easily now, right? The number of handshakes should be equal to the number of segments that we've drawn. So we drew, I'm just going to mark them as we go. So we drew 1, 2, 3. Then we had 4, 5, and 6. So it looks like 6 handshakes, right? That's maybe not the best notation because this usually means something in geometry, right? It means like all of these line segments are the same length, and that's not necessarily the case given the figure that we've drawn. But I was just kind of marking it to say, you know, okay, we counted that segment, so maybe an X would be better. You say we counted that one, so there's 1, 2, 3, 4, and then 5 and 6. So 6 handshakes. Now, I just want to briefly mention that that's not the only way to do this problem, right? One thing that students will do when they see a problem like this is they'll say, well, Adlia needs to shake hands with Benjamin, Christine, and Dari, so that's 3 handshakes. Benjamin needs to shake hands with Adlia, Christine, and Dari, so that's 3 handshakes. Christine needs to shake hands with Adlia, Benjamin, and Dari, that's 3. And Dari needs to shake hands with Adlia, Benjamin, and Christine, that's 3. So it's 3 plus 3 plus 3 plus 3. Or in other words, 3 times 4, which is 12. And they get the wrong answer, right? Now, why are they getting the wrong answer? Because they're double counting all of the handshakes, right? As we said, Adlia shaking hands with Benjamin is the same handshake as when Benjamin shakes hands with Adlia. So if you say 12, you're almost right, but you need to divide by 2 so that you're not double counting all of the handshakes, right? So that's another approach to the problem. You could say, well, there are 4 people. Each of them needs to shake hands with 3 other people, so that's 4 times 3 is 12. But then that double counts the handshakes, so we divide by 2 to get 6. But this way visualizes it, and that's what I wanted to illustrate with this example, is that it's helpful sometimes to visualize things in word problems. Let's look at another strategy. So another strategy is that you could draw something called a tree diagram. This is especially useful if you're having to make a series of choices. So if you have to make a bunch of choices and there's a certain number of ways to make each choice, well then it's drawing a tree diagram. Like if you're trying to figure out how many total choices there are going to be at the end of the day, drawing a tree diagram is a nice way to solve the problem. So this one says, the fixed price dinner at a restaurant provides the following choices. For an appetizer, you can have soup or salad. For your entree, you can have chicken, liver, or roast beef. And for dessert, you can have ice cream or cheesecake. And so the question is, how many different meals can be ordered? Draw a tree diagram to answer the question, right? So let's do it. So a tree diagram is going to look like this. So first of all, you have to choose your appetizer. And for your appetizer, you can choose soup or salad. So I'm going to draw 2 little nodes here. So we'll call it soup or salad. I don't want to have to write out soup and salad every time. So maybe I'll call soup S1 and salad S2 to distinguish between them. So I've got soup and salad. Okay. Now, once you've chosen your appetizer, you have to choose your entree. And there are 3 choices for each entree. So I'm going to branch off in 3 directions from each of these. Right? So I could choose chicken as my entree, liver as my entree, or roast beef. We'll call it roast beef, B for beef. Okay? And the same thing if I choose salad. Okay? So now let's pause here and note that if all we were doing were choosing an appetizer and an entree, well then there would be 6 choices. You could have soup and chicken, soup and liver, soup and beef, or you could have salad and chicken, salad and liver, salad and beef. Right? So 6 choices so far. But then we have one more choice to make. We have to choose a dessert, ice cream or cheesecake. Oh, and I'll say CH for cheesecake, I guess. And ice cream I'll call I. So each one of these now has 2 options. Okay? So ice cream or cheesecake. Ice cream, cheesecake, ice cream, cheesecake, and so forth. So how many possible dinners are there? Well, it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 meals can be ordered, right? Now, once you've drawn that tree diagram, you kind of get some intuition, and you can go back and you can see that, well, of course it's 12, right? Because given your choice of appetizer, you have 3 choices for entree. And since you have 2 choices for appetizer, that means the total number of appetizers and entrees the total number of combinations there would be 2 times 3. And then once you choose the dessert, it's going to be 2 times 3 times 2. Well, 2 times 3 times 2 is 12, right? Okay, so that's a tree diagram. And by the way, like, given any of these outcomes, you can see what the meal is, right? This is soup, liver, and ice cream, right? This one would be salad, roast beef, and cheesecake, right? So you see all the different combinations there. Okay. Another strategy is that you could systematically list out all the options. This is sort of similar to what we just did, but kind of you could organize it into a chart rather than organizing it as a tree diagram. So you can just kind of organize stuff into a chart. So let's do that. It says Nico is considering which optional features to include with his new smartphone. He has narrowed it down to 3 choices: a quick charging battery, multiple windows, and a high-resolution camera lens. Depending on price, he will decide how many of these options he can afford. Okay, so in how many ways can he make his decision? Okay, well, let's see if we can list this out. So now this is one that I need to reread because I'm not sure I've got it. But I think what's happening is that Nico has these 3 features that he can add to his smartphone, or that he can look for in a new smartphone when he goes to purchase one. He might not choose any of them, or he might choose all 3 of them, or he might choose just a couple of them or whatever, right? And that all depends on the price of these features. So it's possible that he might choose none of them. It's possible he might choose 1 of them. He might choose 2 of them, or he might choose all 3 of them. So let's see if we can list out all of the. It says, in how many ways can he make his decision? So let's see if we can list them out. So first of all, for quick charging battery, I'm going to call that B for battery, W for window, R for high resolution. So I'm going to say B for battery, W for window, and R for resolution. Okay. And then here I'm going to try to list out all the possibilities. So if he chooses none, so if it turns out that it's all too expensive, right? All of the features are too expensive, so he doesn't buy any of them. Well, that means that he's not going to get this one, or this one, or this one. If so I guess this row represents the number of features. Number of features he ends up purchasing. And so maybe instead of none, I can call it 0. So it's a little more mathematical. Okay? Number of features, 0. That means he's not getting any of the features. He could purchase 1 feature. Now that could happen in more than one way. That could happen if he gets this one, but not these 2. Or it could happen if he gets this one, but not these 2. Or it could happen if he gets this one, but not these 2. So maybe I'll kind of separate it like this. 0, 1. Okay. I might run out of space, but that's all right. If he chooses 2 of them, now, how could that happen? That could happen if he gets this one, but not that one. I'm going to start making my marks smaller so I can fit it all on here. It could happen if he gets this one, not this one, but this one. Or it could happen if he doesn't get this one, but gets the other 2, right? Okay. And then finally we said he could end up getting all 3 if they're all cheap enough, right? He might get all 3 features. And so that can only happen in one way. That happens if he gets these 3. So now going back to the question, in how many ways can he make his decision? Well, He's got 1, 2, 3, 4, 5, 6, 7, 8 possibilities, right? So there are 8 ways for him to make the decision. Okay. All right, so that's that. How many more of these? I think I have 3 more suggestions. I have 3 more suggestions, so we're about halfway through. So another thing that you can try is you can try looking for a pattern. And here's an example of that. So this pattern here is called Pascal's triangle. It's a famous thing. It's got lots of really nice properties. One of the things that it's used for is to expand binomials really quickly. Like if you had x plus y squared, you might remember from your algebra days that you have to write this out twice and then FOIL it. If you don't remember that from algebra, don't worry too much. But when you write it out twice and FOIL it, you get this scenario, right? And then you get x squared plus 2xy plus y squared. And notice the coefficients here are 1, so you have 1, 2, and 1. Well, that shows up in this row of Pascal's triangle, row 1, 2, 1. So if you wanted to do x plus y cubed, instead of squared, you would go to row 3 and you would get an coefficient of 1x cubed plus 3x squared y plus 3xy squared plus 1 y cubed. Anyway, so that's one of the things that Pascal's triangle is used for. But you don't have to worry about that too much. I just wanted to give you some background. But anyway, this thing is called Pascal's triangle. Now, notice that in Pascal's triangle, each number is the sum of the 2 numbers immediately above it. So for example, 6 is 3 plus 3, right? 3 is 2 plus 1. 5 is 1 plus 4. The outside numbers are all 1s, so you always just put a 1 down the outside rows. But so for example, if we wanted to do row 6, we could do that pretty easily. First of all, we would have a 1 here. Then we do 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And then a 1 on the outside. And that would be row 6, right? And so you could keep doing this. And so you see, it makes doing something like this a lot quicker, right? Because all you have to do is make this little triangle. Well, anyway, our task here says find the total of all the numbers that will be in the 9th row. So find the total of all the numbers that will be in the 9th row. Okay, well, one way that we could solve that problem is we could just make row 7, row 8, and row 9, and then add up the numbers in row 9. But another thing that we could do is we could look for a pattern here. And in particular, what I want to suggest to you is that we look at the sum of each of these, of each of the rows, and see if we can find a pattern. So I'm going to see if we can notice a pattern here. So for row 0, the sum is just 1. For row 1, the sum would be 1 plus 1, which is 2. For row 2, the sum would be 1 plus 2 plus 1. That's 3 plus 1 is 4. Okay. Interesting. For row 3, we do 1 plus 3, which is 4, plus 3 plus 1, that's another 4. So 4 plus 4 is 8. Notice what's happening. We're doubling each time, right? We went from 1 to 2, from 2 to 4, from 4 to 8. I have a feeling the next one's going to be 16. I'm just going to guess that it's 16. Let's verify if it is. 1 plus 4 is 5. 5 plus 6 is 11. 11 plus 4 is 15. And 15 plus 1, sure enough, is 16. So this is nice. This means that I don't have to actually write out the next rows. I can just keep doubling, right? 16 times 2 is 32. 32 times 2 is 64. That's row 6. For row 7, I would double 64 again and get 128. That's row 7. For row 8, I would double again and get 256. And for row 9, I would double one more time and get 512. You're welcome to use a calculator, by the way. So don't freak out if you think I expect you to do this all in your head. But 512, that's when we get to row 9, right? When we get to row 9, you say dot, dot, dot. When we get to row 9, the sum is going to be 512. Okay? So looking for patterns is kind of a useful thing. Now, something else that I'll say about this is this actually bleeds really nicely into the next suggestion, right? The next suggestion is that you try to solve a simpler version of the problem, right? So what does that mean in the context of this one that we just looked at? Well, what made this problem sort of maybe not difficult, but definitely tedious, what made it tedious was that, well, there was so much additions that we would have to do in order to get to the 9th row, and then by the time we got to the 9th row, we would have to add up all those numbers, and man, that would have taken us a while, right? But notice that what we did in looking for a pattern is we started trying to solve easier problems. We said, well, forget about row 9. What's the sum of the numbers in row 0? That's a lot easier, right? What's the sum of the numbers in row 1? That's a lot easier. What are the sum of the numbers in row 2 and 3 and 4? That's a lot easier. And by the time we finished solving all those easy problems, then we were able to notice the pattern that allowed us to solve for the larger row without having to do so much work, right? So that's a good strategy in general, right? Looking for patterns is good, but also just trying a simpler version of the problem is a good idea. So another example of that would be if we went back to this first one. Remember the handshake example? Now in this example we only had 4 people, but imagine if you had 100 people, right? If you had 100 people, they were all trying to shake hands, drawing 100 dots and trying to connect all of the lines. I mean, that would be a lot of work, right? But what you could do is you could solve the problem for 4 people. And notice that it's 4 times 3 divided by 2, as we talked about a second ago, right? And then you could say, well, so what would it be if you had 5 people? And you could draw 5 dots. And what you would notice is that for 5 people, you would get the same thing. It would be 5 times 4 divided by 2. And so if you had 100 people, it would be 100 times 99 divided by 2, right? So solving simpler versions of the problem is a good strategy. Here's another example of that strategy in action. So this one says, Brianna's car gets 23 2/3 miles per gallon of gasoline. One day she starts driving. She isn't being careful and she runs out of gasoline on the road. And she knows from checking her odometer that she traveled 107 3/5 miles. How much gas was in her car at the start of the trip? So, in my experience, students freak out as soon as they see fractions, right? As soon as they see fractions, they just, I don't know what it is, but fractions, they just freak students out a lot. And so it's the fractions that are making this problem difficult. Like if you read through that and you were like, I'm not sure what to do. Do I add those numbers? Do I multiply them? I mean, what am I supposed to do with these numbers? Do I subtract them and then do something else? I mean, what do I do with them? If you're completely lost like that, I would say it's most likely because of the fractions. So a simpler version of the problem would be to go back through this problem and replace these fractions with just easy numbers, right? So it says Brianna's car gets 23 2/3 miles per gallon of gasoline. Forget that, right? Well, instead of thinking of like 23 2/3, let's just say it's 20, right? Brianna's car gets 20 miles per gallon. One day she starts driving. She isn't being careful and she runs out of gasoline on the road. She knows from checking her odometer that she traveled 107 3/5 miles. Okay, so again, forget that weird complicated number. Let's say that she traveled 80 miles. And the question is, how much gas was in her car at the start of the trip? So we know that Brianna's car gets 20 miles per gallon. If she travels for 80 miles, how much gas did she have, right? How much gas did she use? So her car gets 20 miles per gallon, and she traveled for 80 miles. How much gas was in her car? Well, it must be 4 gallons of gasoline, right? Because her car gets 20 miles per gallon, but she travels a distance that's 4 times as much as that. That means that if she only gets 20 miles on 1 gallon of gasoline, then in order to go 80 miles, she would need 4 times as much gasoline, right? So she would need 4 gallons of gasoline. There are a whole bunch of ways that you could think about this. You could say, well, what times this number equals that number, right? What times this number equals that number? Well, another way to say that is division, right? So you would say it's 80 divided by 20, that gets you 4, right? 80 divided by 20 is 4. So based on that kind of simpler version of the problem, we can go back to the original now and say, well, when I replaced this with 20 and when I replaced this with 80, in order to find the answer, all I did was this one divided by that one. So it should be the same thing now that they're fractions, right? It shouldn't be any different. So instead of it being 80 and 20, now it's 107 and 3/5 and 23 and 2/3. But still, my answer should be 107 and 3/5 divided by 23 and 2/3. And now here you might have to flex your pre-algebra muscles, right? You might have to remember how we do division with fractions and mixed numbers and all that. So first of all, like I said before, you're welcome to punch this into your calculator. If you're going to punch it into your calculator, probably the way that you'd have to do it is you'd have to say 107 plus 3/5, because that's really what 107 and 3/5 means. And then you'd have to divide that by 23 plus 2/3. But generally speaking in math, if a problem is given to you in fractions, you should give your answer in fractions. So if you punch this into your calculator and it gives you a decimal, you got to figure out how to change that back into a fraction, okay? So anyway, but you could punch this in. Make sure to use the parentheses, otherwise you're going to get the wrong answer. If you just punch it in without the parentheses, it's going to do 107 plus 3/5. So far, so good. Then it's going to divide that by 23, which is not what you want. And then it's going to add 2/3 to your final answer, which, again, is not what you want. You want to divide by this thing. So you have to use parentheses here, use parentheses there, then divide them. But if you wanted to do it by hand, you would change this into an improper fraction. So we do 107 times 5, and then add the 3. I'm using my calculator now. This is 538 over 5. Here you do 23 times 3. Plus 2, you'd get 71 over 3. And then to divide fractions, what you do is you flip the second one over and you change the division to multiplication. So 538 divided by 5 times 3 over 71. And when you multiply fractions, you just multiply straight across, right? So 538 times 3 is 1,614. 5 times 71 is 355. If your calculator is fancy enough, then it'll reduce this for you. Oh, actually, this fraction is not reducible, so it doesn't reduce at all. But you do want to change it into a mixed number, which means you need to figure out, well, how many times does 355 go into 614? And that would be 4 times. 355 times 4 is 1420. 1614 minus 1420 is 194. So you should get 4 and 194 over 355. Gallons. This is how many gallons she had in her tank. This is approximately 4.5465, we'll say, gallons of gas. Okay? But anyway, so all this math was kind of like, whatever. You can use a calculator. I'm okay with you using a calculator. You could have just done this and gotten straight there. But as far as setting it up is concerned, it was easy once we solved an easier version of the problem, right? Just 80 divided by 20. So it's 107 3/5 divided by 23 2/3. Okay, one more strategy that I want to talk to you about is guess and check. In algebra class, we typically discourage students from using guess and check. And the reason for that is because when we're teaching you algebra, we're trying to show you examples of things that actually use algebra in the solutions, right? And so we want you to use the algebra in order to solve the problem. But also algebraic solutions are nice because oftentimes they'll get you the answer quicker than just guessing and checking over and over and over again. That said, in certain scenarios, guess and check is really pretty nice, and it can be a lot easier than algebra. And worst case scenario, you do guess and check and you can't find the answer, but at least you develop some intuition, right? That'll help you to solve the problem in a different way. So let's go through this one. It says, Manuel has 85 cents in nickels and dimes. He has 12 coins in total. How many of each type of coin does he have? Okay. So he has so you can imagine, like, if he has 3 nickels and 3 dimes, well, first of all, that doesn't add up to 12 coins, right? But 3 nickels is 15 cents, and 3 dimes is 30 cents, and 15 cents plus 30 cents is 45 cents. So that's kind of the situation that we're dealing with here, right? So if I wanted to solve this by guess and check, first of all, I want to kind of organize my guesses. So I'm going to make a little table, and I'm going to say number of nickels number of dimes, and then the value of those coins, right? The total value. Maybe I should call it total value. The total value of the coins. Now, we know that the number of nickels plus the number of dimes has to equal 12. He has to have 12 coins, right? So we're not going to guess 3 and 3 because 3 plus 3 is 6, right? We need to have 12. What we could guess is maybe 6 and 6. Now, 6 nickels. A nickel is worth 5 cents, so 6 nickels is worth 30 cents. And 6 dimes is worth 60 cents. So if he has 6 nickels and 6 dimes, then he has 6 times 5 plus 6 times 10. That's 30 plus 60, which is 90 cents. That's too much, right? Because he's only supposed to have 85 cents. So what does that tell us? Well, dimes are worth more than nickels. So if this was an overestimate, then probably he has fewer dimes than what we wrote down here. So let's try with 5 dimes. Now, if he has 5 dimes, how many nickels should he have? Well, he has to have 12 coins in total, right? So if he has 5 dimes, then he must have 7 nickels, because 7 plus 5 is 12. And now we can try, what's the total value of the coins now? It would be 7 times 5, right? Because nickels are worth 5 cents. Plus 5 times 10, because dimes are worth 10 cents. Okay, this would be 35 plus 50. And that comes out to 85. Oh, and there you go, right? Because we were told he has 85 cents. And so that's the winner, right? We can stop guessing because we found our solution. All right, so we would say Manuel has 7 nickels and 5 dimes. And that's the answer to that question, right? So guess and check, right? It's not a horrible thing to do. Like I said, worst case scenario, you're unable to find the answer this way, but at least it gives you some at least it gives you some intuition, right? If you were trying to solve this algebraically, you could say, let's call the number of nickels n and the number of dimes d. Then the total value of the coins would be number of nickels times 5 plus number of dimes times 10, or in other words, 5n plus 10d. And you could use this in some other equation, like you know that the number of nickels plus the number of dimes has to be 12, so n plus d equals 12. So you would also get n plus d equals 12. This needs to equal 85. And then you've got a system of equations, and you can solve the system, blah, blah, blah. But guess and check is quicker in this scenario. So that's that. Those are all the suggestions I have for you. Of course, we're just scratching the surface there, but hopefully it gives you some ideas, some things that you can try out as you go to solve problems. So that'll do it for this section.